Greetings everyone and welcome to the fifth lecture of the logic part of Comp 0003. In today's lecture we're going to begin a new topic, which is first order logic, and that's going to occupy I think the next 4 or 5 lectures. Now first order logic builds on propositional logic, so we're kind of starting somehow from propositional logic, but it's much more powerful in that it lets us express properties of objects in some imagined universe, and also to quantify over those objects. So we can say that all objects in the universe have a property, or some object does, or everything with a certain property also has another property. So that's going to be super useful, and once you have first order logic, you can kind of write down lots of sort of familiar mathematical content and proofs. You can formalize arithmetic in it, and this kind of thing. So remember that I said that at least from the point of view of this course, a logic has got 2 major components. The first is the syntax of the logic, which explains what does and does not count as a formula. And then the logic also has a semantics in which we explain how to read or understand formulas of the logic. So in today's lecture, we're going to focus almost exclusively on syntax, which is quite a bit more complicated than in propositional logic. We'll keep the connectives, but we're going to introduce some predicates and terms and this kind of thing. So it will look a tiny bit like set theory, perhaps. And we're also going to add quantifiers. Oh yes, but also at the end of the lecture, I might try and give you at least some idea of how to read the formulas just in an informal way by showing how to try and translate some English language sentences into predicate logic or first order logic formulas. Okay, so I think that's pretty much it. Let's go to the slides, and I might see you back here in a bit, or maybe not. We'll see how I feel. Okay, so before leaping in with the kind of formal definitions of everything, I wanted to start just by giving a kind of quick overview of first order logic, and just give you somehow the headlines. So the first headline is that instead of the propositional letters or the proposition variables P, Q, and R, and so on that we had before, we're now going to have these more general predicate formulas, which are of the form P with some arguments, and so here. The symbol, the predicate P, has n arguments. So P is a predicate symbol. It takes n arguments, and the arguments are given by these T's. The T's are called terms, and you build up terms sort of a bit like you would in standard mathematics from variables and function symbols. So we're going to have sort of variables x, y, and z, and so on, and these can all be arguments of predicates, but also we can have things like f of x or g of x or f of x and y, or x plus y, and all that kind of thing. So we're going to be able to sort of build up terms, and these terms are the arguments of predicates. And that's the main change, or the first main change to the syntax. And the second big change is we're going to add these 2 quantifiers. The first is written as this upside down A with a variable name x, which might be x or y or z. So upside down A and a variable means for all, and then the variables. So in this case, this is for all x. And so whenever you have a formula that has sort of for all x at the start, you understand it as meaning for all x, it is the case that blah. And the second quantifier is this backwards E, and it should be read as there exists. So this is read as there exists an x such that whatever. So just as one kind of simple example, here's our Aristotelian syllogism from the first lecture again. All men are mortal. Socrates is a man. Therefore, Socrates is mortal. Well, as I think we remarked in the first lecture as well, there's definitely a universal statement right here saying everything which is a man is also mortal. So we have 2 properties here, the property of being a man and the property of being mortal. So these will become predicate symbols in our formula. We also have Socrates, which will be it will become a term. If you like it, it will be what we call a constant. So we could render this argument in first order logic in the following way. The first line, all men are mortal. For all x, if man x, so man is a predicate and it takes one argument, which here is the variable x, implies mortal x. For all x, if x is a man, then x is mortal. Second line just becomes man of Socrates, so it's just a predicate formula on its own, and then the conclusion is the same, mortal of Socrates. So yeah, here we have two predicates, man and mortal, and in this example we have two terms. We have the variable x, which is used to make the quantified statement at the top, and we have Socrates, which is a constant. Just to carry on for a little bit, I'm not going to talk about semantics in this lecture, but I think it's important to be thinking about it ahead of time, is when we had just simple propositional variables, well, we said there's only really two cases you have to worry about. Either the proposition is true or it's false. And if you know whether the propositions are true or false, then you can work out whether a formula of propositional logic is true or false as well, using the tables or another method. But in order to understand whether a predicate formula, P with some arguments, is true or false, well, it very much depends. It depends on what the predicate means, and it depends on what the terms mean. So in order to define the truth value of this guy, we first of all have to define what it is we mean by the terms that are appearing in the formula and by the predicate symbol itself. So very roughly speaking, we're going to talk about, instead of a valuation of the proposition letters, we're going to talk about a model for first order logic, and a model is going to basically explain to us, or it's going to define what we mean by all the variables, all the function symbols, and all the predicate symbols that are kind of occurring in a formula. And then once we have such a model, we can define the truth value of a formula in that model. So of course, for any given formula, or indeed any given language which contains some predicate symbols and function symbols, there are in general going to be many different models or many different ways of interpreting those symbols. Well, just because a symbol can really mean whatever you decide that it means, given certain restrictions, which I'll describe in a later lecture. Okay, so let's move on and talk a little bit about the syntax, but now I'm going to define it formally. So the first thing, I'm going to assume that we have an infinite set of variables, x, y, and z, and so on. Generally, I'm going to try to remember to write variables using these lowercase letters and save my capital letters for the names of predicates. So then, a so-called first-order language, which I'm writing, usually use the symbol Greek sigma, has got like two components in it. The first is a set of function symbols, so I'm going to write that set of function symbols as curly f, and we can have some number of function symbols. It could even be an empty set. We just have some number, and the important thing to remember here is that all the function symbols have got what we call an arity associated with them. So an arity is a natural number greater than or equal to 0, which is the number of arguments that the function takes. So a function could be unary or binary or ternary, or even it could be n-ary for any kind of n. In the special case where the function symbol has arity 0, so it takes no arguments, it is then called a constant symbol. So just like the Socrates that we saw in the previous example, a constant can be seen as a function that however doesn't take any arguments. And the second thing is that we also have a set of predicate symbols. And again, predicates could be unary, like man or mortal in the previous example, or they could be, for example, binary. That's very common when we're talking about relations between objects, X loves Y and that kind of thing. In the special case where a predicate symbol has arity 0, so it doesn't take any arguments, again, it can then just be seen as a proposition. So a proposition letter is kind of a special case of a predicate formula where the predicate doesn't take any arguments. So the first order language, I said it's given by two components, this set F of function symbols and this set P of predicate symbols. So I'll generally write for a first order language, sigma equals F and P. So functions and predicates. All right, so now let's go and look at a couple of examples of first order languages. And our first example is a first order language for so-called piano arithmetic, named after the Italian mathematician Peano, who gave axioms for arithmetic for almost the first time in the late 19th century. So remember that a first order language has got two components, the set of function symbols and the set of predicate symbols. So here my language, which I'm writing with a little PA for piano arithmetic, has got this set of function symbols, so 0, S, plus and times, and two predicate symbols, equals and less than. Now, let's just remind ourselves that all the symbols have got to have an arity, which is the number of arguments they take. And so this shouldn't surprise you at all. So the symbol 0 is a constant symbol. So it's a function of arity 0. And obviously it usually means the number 0. That's why we would normally read that symbol. The next function symbol is S. That's a unary function symbol. It has arity 1. And S in piano arithmetic is the successor function. So it's the function that takes a number and returns the next one. So we can think of it as being like x plus 1. So S of x is x plus 1. We also have symbols plus and times. These are both binary function symbols, and obviously they usually would stand for addition and multiplication, respectively. And we also have two predicate symbols, equals and less than. Now, these are both binary predicates. They take two arguments each. And obviously, equals usually means equals, and less than usually means less than. So it's an inequality predicate. It's a good moment, I think, to remark that although we normally write a function symbol applied to arguments, we'd normally write it as like f of x, y, z, etc. We can also sometimes write binary symbols using an infix notation where we write the function symbol in the middle. Now, obviously, plus and times are perfect examples of this, because in arithmetic we always write x plus y. We don't usually write plus of x and y. So sometimes we might do that. And the same is true for predicate symbols as well. We might write the predicate symbol in the middle and write sort of x equals y rather than equals of x and y. Okay, so so that's our first language. 4 function symbols, which include one constant and 2 predicate symbols. So this is a case where I've thought about arithmetic, which is a standard logic-y thing, but we don't have to take a language that talks about arithmetic or uses conventional symbols at all. We can take whatever symbols we want. So here I've taken an example which is supposed to represent a first-order language for my MP3 library. I don't know whether people still have MP3s or not, or whether all the kids have something else now. I guess they're all probably streamed. But anyway, I've got an MP3 library, and so I've come up with this kind of toy language for talking about it. So I'm going to have a bunch of constant symbols. I might have more, but here I've written down 2 of them. They're constants. They're function symbols with arity zeros, and I'm going to use them to kind of denote objects in my universe, which are going to be the songs. So here's Lonely Avenue, which is a Ray Charles song, and here's 007 Shantytown, which is a Desmond Dekker song. Okay, and then I also thought about a couple of functions. If you imagine that all the songs in my library are written down in some order, or they, stored in some kind of order, then perhaps I can have two functions, next and prev. They're going to be unary functions, so arity1, and the idea is that they should, given a song, they should return the next song. Well, next does, and prev returns the previous song. And you can kind of imagine that perhaps if you get to the end of the list, then next will kind of loop around and give you the first one back again, or something like that. And then I also thought about some predicates that you might have on my MP3 library, or the songs in my library. So I could have predicates that represent genres. So two genres are blues and reggae. They're predicates of arity1. So blues of X is supposed to represent the property that particular song belongs to the blues genre, and the same for reggae. And then I thought about a couple of binary predicates as well. So I used this kind of this triangle symbol to mean better than. So I'm thinking of this being written infix as well. So X triangle Y is supposed to be kind of interpreted as X is better than Y, according to perhaps my own personal rating of the songs or something. And this kind of twiddle or tilde, I'm also thinking of being infix, and I'm going to use that to mean that two songs are similar. So X twiddles Y might mean that X and Y are similar songs. So that's an example. We also saw other examples where we had man and mortal, and they were predicates, and this kind of thing. You'd have Socrates, the name of a philosopher. So hopefully you can kind of see that you can think of first-order languages that might describe a whole bunch of universes or situations. Okay, so now I'm going to give the inductive definition of a term of a given first-order language sigma. So I suppose that I've already fixed my first-order language, so I have my function symbols and predicate symbols, and now I'm going to explain inductively what I mean by a term. And when I say inductively, I mean it's going to be similar to the definition of a formula in that I'm going to explain how to build up bigger terms from smaller ones. So first of all, any variable x or y or z, etc. is a term. Variables are terms. And the second rule is take any function symbol in the language. The function symbol is going to have an arity, which is, let's say, k. Now, supposing that I have terms t1 up to tk, so I've got k terms, then the function symbol applied to those k terms is a term as well. So in other words, if I've already constructed k smaller terms, then f applied to those terms is a term as well. So, for example, if f has arity 1, then f of x is a term, because x is the variable x is a term, so fx is also a term by this definition. By the way, this second clause also implies that any constant symbol is a term as well. So constants are also terms. That's because a constant is a function symbol in sigma for sure. It has arity 0, and then this part just goes away because these terms t1 to tk just disappear, because obviously it doesn't need to take any arguments. So then the constant symbol applied to no arguments is a term as well. So going back to our language for arithmetic, which was our first example, the following things are all terms. So 0 is a term, and in particular s of 0 is a term as well. Or x plus successor of y, that's a term. Again, and you can also see that all the subterms of this thing are terms as well. So successor of y is a term, x is a term, and z times the successor of x plus the successor of y. So in other words, you can apply functions to constants and variables in the expected way, and you can nest functions. All you have to do is make sure that you're kind of respecting the arities of the functions. So functions have to be applied to the correct number of arguments. But apart from that, you're all good. And in my language of sort of MP3 songs, then we can think about terms such as the following one, next of x, or prev applied to 007 Shantytown, or a whole bunch of nested functions, next of prev of prev of next of y. By the way, nothing else is allowed to be a term. So you're not allowed, so for example, terms definitely can't contain predicate symbols or anything weird like that. Okay, so that's the definition of a term. Now we can give the definition of a formula. So again, I suppose here that I've already fixed my first order language, so we know what we mean by terms. So the main changes from propositional logic, as I said before, is that we're going to replace propositions by predicate formulas, and we're going to add the two quantifiers, which are for all and exists. So P of T1 up to Tk is a predicate formula, so it's a formula, and sometimes we call it a predicate formula or sometimes an atomic formula. So this supposes that P is a predicate symbol in the language, and that T1 up to Tk are all terms in the language. So provided that's true, then this guy is a formula. Then we're going to have all the connectives of propositional logic. So negation, conjunction, disjunction, implication, and by implication or equivalence. So if I already have some formulas, then I can build up larger ones by applying the connectives. And finally, the quantifiers. If A is a formula, then so is for all x A. And I'm putting the A in brackets here. This is supposed to indicate the scope of the quantifier. We'll talk more about that shortly. And if A is a formula, then exists x A is a formula as well. And here, although I've written x, I mean that it's also good for any variable. So exists y A is a formula as well. Oh yeah, and here's just written down explicitly the comment that P has to be a predicate symbol and T1 up to Tk are supposed to be terms. So that was the kind of somehow official syntax of formulas, but we also kind of adopt some notational conventions or abbreviations just to try and cut down on notation and brackets and this kind of thing. So there's 2 points I wanted to mention. The first thing, which is really common, is that if you write a formula and the outermost connective is a quantifier, so the formula is of the form for all x something or exists x something, or even a block of nested quantifiers for all x exists y, for all z, blah, 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 then quite often I'll drop these outermost brackets and just write a dot after the quantifier as well, which is a bit easier to read. And whenever you see the dot, then you kind of mean, then what that means is that the scope of the quantifier or the brackets are supposed to be around the entire rest of the formula. So that's what that means. So if I write the dot, it means for all x and then the whole next thing, all the rest of the formula in brackets. Also, there's the usual precedence order for propositional connectives. So negation binds tighter than the other connectives. I don't think I really used this before, but quite often we also consider or and, so disjunction and conjunction, to bind tighter than implication and by implication. So typically when you write down this formula, A and B implies C, then you really mean A and B implies C, and not A and brackets B implies C. Usually I think I'll try and keep the brackets in just to keep things unambiguous, but I might drop them sometimes. Right, next, scopes. So I said that quantifiers have a scope, and so essentially I'm just going to flick back here. So the scope of this quantifier here, for example, the scope of for all x A in brackets is that so it's basically everything in between the brackets. So it's the formula A. Or in the case where you have a dot, the scope of the quantifier is everything that comes after the dot. Okay, so let's go back. That means that we have so-called bound and free occurrences of variables in formulas. So an occurrence of a variable x, because there might be multiple occurrences in one formula, and an occurrence is called bound if that variable occurrence falls within the scope of a quantifier with the same name, so for all x or exists x, and if it's not in the scope of any quantifier, then the occurrence is called free. So let's see some examples which come from my arithmetical language. Here we have the formula x equals successor of y. So remember that x and sy are terms, and equals is a predicate symbol of arity2, so x equals sy is definitely a formula. But here there are no bound variables because there are no quantifiers. So here x and y are both free variables in this formula. Next example. Exists x dot x equals successor of y. So this is the same formula with an existential x quantifier on the front of it. So here this quantifier binds this occurrence of x because this x is in the scope of this existential quantifier. This y is also within the scope of the quantifier, but it doesn't have the same name, and therefore this occurrence of y is still free in that formula. So we have one bound occurrence of x and one free occurrence of y. The next example, exists x, x equals successor of x. So here we have two occurrences of the variable x, and they are both bound by this quantifier. They're both within the scope of this exists x, so they are both bound by this quantifier. And when I say bound, by the way to think about it informally is when you say there exists an x such that blah, then whenever you say something in the scope, which is the blah, then whenever you say x, you mean that you're referring to the same x that you were talking about when you said there exists an x such that. Next example. Exists y, x equals successor of x. Okay, so again here there are actually no bound variables because although there are two occurrences of x, they're within the scope of this quantifier here. Again, the quantifier does not have the same name. We have exists y, so there are no bound variables and two free occurrences of x here. Here's an example with two quantifiers. For all y, exists an x such that x equals sy. In this example, the occurrence of x is bound by this exists x, and this y is bound by the for all y. So this is an example of a formula with two different bound variables. Okay, and now a final example. Here's a more complicated guy. For all y, either exists x, x equals sy, or x plus y equals 0. So here, this formula has a universal quantifier on the outside, and then the main connective is actually the disjunction, and one argument of the disjunction is this existentially quantified statement, and the other is this formula here. So at least the y's are easy to sort out because these two occurrences of y are both within the scope of this quantifier, since the scope, remember we've got the dot here, so the scope of this for all y is the whole formula. So for sure these two y occurrences are bound by that quantifier. The x's are more complicated. Here you'll see that we have exists x, and the scope of this quantifier, this exists x, is this formula here, which means that this occurrence of x, the first occurrence in red, is bound by the quantifier, but this second one isn't. So this formula has two bound occurrences of y, one bound occurrence of x, and one free occurrence of x. It's a pretty strange formula and not something you would ever really want to write, I don't think. So most of the time it shouldn't be too confusing, and the scope, both the scope and the binding status of variables should be quite clear most of the time. And if it's not clear, then it's probably a formula you've written down and you've made bad notational choices, and so it's your own fault. Okay, so just to say as well that a formula that does not have any free variable occurrences is often called a sentence. That is somehow because formulas without any free variables somehow correspond to things that like make sense as sentences if you were going to try and say them in English or as mathematical statements, whereas things with free variables floating around them are often a bit weird. They've got free x's and y's that don't really refer to anything, and so they're a bit strange. Okay, so that covers the syntax of first-order logic. We've explained what does and does not count as a formula in some suitable first-order language. Defining the semantics of formulas is quite complicated and will take, I think, 2 or maybe even 3 lectures. But one thing that we can do straight away is see how we might translate English sentences into formulas of first-order logic given some suitable first-order language, so we can invent predicates and function symbols to suit ourselves. It's important to say that none of the kind of guidelines or examples I'm given, they're not rules for doing things. There are many ways in general of translating English formulas into first-order logic, and in particular, because there's lots of formulas that are equivalent to each other, there's lots of different ways of writing down things which are logically the same, even though they might look quite different. And we've seen that already in propositional logic. So I think it's also it's probably worth noting that translating English into first-order logic is very much the sort of thing that you might be asked to do in an exam. I think there's been a question on it in most of the previous years. So pay attention and let's go and have a look at some translation examples now. Okay, so first I think a few general guidelines will be helpful. So if you look at an English sentence, in propositional logic, I asked you to start by identifying the propositions and then try to identify the connectives in the statement as well. That will still be true to a certain extent for first-order logic. We're still looking for the connectives and this kind of thing. But we will generally want to try and break down the propositions a bit more. So in particular, predicates in English will usually be rendered in first-order logic as predicate symbols. So by a predicate in English, I mean a word that describes a property of objects or a relationship between objects. So for example, if I say, my car is red, then the property of being red is a kind of standard kind of thing that you would render as a predicate symbol. Or if it's something like James loves his cat, then the property of something loving another is a predicate as well, or a relation in English, and that would be mapped as a 2-argument predicate in first-order logic, typically. Nouns, names for things, and especially proper nouns, such as James or Boris Johnson or my cat Shadow, they will typically come out as constants in first-order logic. And nouns with prepositions are quite often rendered as functions. So for example, if I say the sum of x and y, then the sum of will usually be a function, like an addition function. But it's probably true of other things. If I even say something like the bar of the pub, then you can think that the pub is an object, a constant, and bar of is a function. Although, that's not the only way of doing things, but it's often quite natural. Fairly obviously, whenever you make a universal statement or a generalizing in English, so if we say all things are like this or everything is like this, then that's going to be rendered using some kind of universal quantifier and some kind of existential claim. Say there is something, there are something, or some things are like this. Well, that will be rendered using an existential quantifier. Let's go on and see some examples. Let's start with something simple. James is Scottish, and so is his father. Well, okay, so there's one predicate in this sentence, which is the property of being Scottish, so that will naturally become a predicate symbol. We have the proper noun James, and so that will typically become a constant, in the same way as we had, Socrates is mortal, and that kind of thing. And so is his father. So we can also say that, James's father could be a constant symbol in the language, but actually, assuming that people only have one biological father, I could also render it as a function. Father applied to a person gives you back a person as well. So here's how I've chosen to render this in first order logic. Scottish of James, I've written James with a lowercase to indicate that it's a constant, and Scottish of father of James. So here James is a constant, father is a unary function, and Scottish is a predicate. Okay, next example. All Scottish women have red hair. This is believed in some parts of the world. It's not in fact true. But obviously we still have the property of being Scottish, but we also have the property of being a woman and the property of having red hair. And it's a general statement. So one way of reading it is, for all X, if X is Scottish and X is a woman, then X has red hair. And that's exactly how I'm going to choose to write this down. For all X, woman X and Scottish X implies red hair of X. So notice here that all these X's are bound by the quantifier. So when I say it, so in other words, this X here, when I say for all X, I'm referring to this whole formula. So I'm referring to this one, and this one. Next, there is a monster living in Loch Ness. Obviously that's a true statement. And it's an existential statement because it's saying there is something. Now, we could imagine that the monster is a predicate. I think probably yes. I think the property of being a monster is a property, and living in Loch Ness is a property as well. But also something living somewhere is also a property, and so I've chosen to render this, I think, as a binary predicate. Exists X, there is something in the universe such that X is a monster, and although I could have had one unary predicate saying lives in Loch Ness of X, I've chosen to have Loch Ness as a constant, and I said lives in of X and Loch Ness. So I've chosen to do it that way. Okay, more examples. Haggises are larger than rabbits. For any international students watching this video, a haggis is a small rodent mammal native to the Scottish Highlands. We all eat them on Burns Night to celebrate the birth of Scottish poet Robert Burns. We drink whiskey and recite poems. It's all very good. And this is not quite a true statement. Haggis is actually about the same size as rabbits. Anyway, so we have three predicates in this sentence: the property of being a haggis, the property of being a rabbit, and those are both unary predicates, and the property of something being larger than something else. But when I say haggises are larger than rabbits, I'm really making a universal statement. I really mean that every haggis is bigger than every rabbit. So actually, I'm going to have to use two quantifiers here. For all objects X and for all objects Y, so for all X and Y, if X is a haggis and Y is a rabbit, then larger than of X and Y. But by the way, this shows you that the order that you write the arguments in a predicate is really going to matter. Because obviously X being larger than Y is not the same thing as Y being larger than X. So, I mean, obviously if I'd written it the other way around, then I'd be saying that rabbits are bigger than haggises. But otherwise, this example is quite similar to the thing of the example of all Scottish women have red hair. So it's a universal statement with an implication inside it. For a lot of generalizations that are rendered this way, you're saying for all things of a certain type, and by a certain type, you're saying this is the left-hand side of the implication. This is like the assumptions. Then this relationship holds. Next example, haggises live on hills. True. So here, this is kind of, you have to think a little bit about this one, because I'm not saying that I'm making a universal statement about haggises, but I'm not making a universal statement about hills. I'm not saying that every hill has got haggis living on it, nor that all the haggises live on one exact hill. So what I really mean is, for every haggis, you can find a hill on which that haggis lives. So I'm going to render this in the following way. I'm making a universal statement about haggises. So for all x, if x is a haggis, then something. Well, and what's the something? This says all haggises do whatever the right-hand side of this formula is. So I'm going to say for every x, if x is a haggis, then there exists a y, which is a hill. Not this, so for every haggis, possibly a different hill, but for every haggis there is a hill, and x lives on y. So the haggis x lives on the hill y. Okay, and just one more example, I think, to finish off. There is a haggis that is larger than any other. So there is one largest haggis. I suppose that is probably a true statement at any given moment in time. So here there's this is a mix of existential and universal claiming, because we're saying, for sure we're making an existential claim. We're saying there is a biggest haggis, but biggest means that for all other haggises, they must be smaller than that one. So this will have nested quantifiers as well, but they'll be nested the other way around. So there is an x that is a haggis, and for all y, so what I want to say is all other haggises are smaller. So here I'm using my equality predicate, because obviously that biggest haggis is not bigger than itself. So the any other means all the different haggises. So for all y such that not y equals x, so for all haggises which are not x, or not equal to x, and y is a haggis, then x is larger than y. So sometimes you have to be careful about doing this, about specifying, if you want to say that some object that you're claiming the existence of has some relationship to all others, such as saying there's the smallest prime number, or there is no biggest prime number, or something like that. You have to be very careful about saying that you don't mean you sometimes don't mean the variable which has been existentially quantified to begin with. All right, and that's the end of the lecture. Hooray! Thank you for listening. In the next lecture, we'll begin looking at the semantics of first-order logic, so I'll begin explaining how to give an interpretation and a truth value to the formulas in first-order logic. I think that's about everything, except to say that if you are watching this in January, as you might well be, then don't forget that Burns Night is on the 25th of January, and so you should get hold of a haggis and some neeps, which are mashed up turnip and swede, and make some tatties, which is mashed potato. So lots of mashed things. Get some whiskey, get a book of Burns poetry, maybe get on Zoom with your friends or something. And have a nice time. So until next time, cheers.